In this next lecture, we're going to discuss reflection and refraction when a plane wave is incident on an interface between two materials. We're going to be looking at two lossless materials, so the wave impedances and propagation constants will all be real. All of this can be very quickly generalized to deal with lossy materials just by allowing the permittivities, permeabilities, impedances, and propagation constants to become complex. It's all very straightforward, but we're not going to worry about those things because the main physics is captured in the interface between lossless materials, I'm sorry. Here are our learning objectives for today, and it's important that you understand something about today's lecture. The two main objectives to take away from today's lecture are, first of all, to be able to understand the polarization decomposition that we do at an interface. When we have a plane wave incident on our interface, we have to do a specific polarization decomposition in order to be able to solve the problem. And so students need to be able to identify the TE and the TM plane waves at the interface in order to do that composition and to be able to use the formulas. This is also very closely related to the way we're going to talk about propagation and waveguides in the lectures that come. The second piece is that you need to be able to understand the physics of wave interaction with the boundary, and you should be able to apply the Fresnel reflection coefficients. Now, in today's lecture, I'm actually going to derive. I'm going to go through the derivation. The derivation's in your textbook, actually both of your textbooks, slightly different presentation. I'm going to talk you through them today. Don't expect you to be able to derive these yourselves, but you should be able to understand what the steps are in the process, how we write down the waves, how we apply the boundary conditions. And then, of course, you have the skills to be able to do the algebra to solve for it. But the key thing that you need to be able to do at the end of today's lecture is to be able to apply the results. So if you don't quite understand the full derivation, that's okay. Do as best you can. But it's important that you understand how to use the result of this. And this is a long lecture, so be prepared. The first thing we need to do is we need to talk about something called the plane of incidence. The plane of incidence is our reference plane that we use to define our polarization states. And the plane of incidence is defined by two vectors. What we have here is we have an interface, and we're going to assume that we have an interface between two materials, medium 1 on the left, medium 2 on the right. And we have a plane wave coming in, traveling in this direction. That plane wave makes an angle theta incident with respect to the surface normal. And in this case, we have our surface normal pointing from medium 1 into medium 2. Okay? So there are two vectors that are important to us. Here I've got a unit vector pointing in the direction of propagation, and here I have a unit vector pointing normal to the surface. And these two vectors define the plane of incidence. If I have two vectors, right, that defines a plane. If I have these two vectors, it defines a different plane. Right? So two vectors uniquely defines a plane, and in this case, it's the plane of the screen. So something that's in the plane of the screen is parallel to the plane of incidence, and something that's out of the plane of the screen is perpendicular to the plane of incidence. We're going to assume that the interface exists here at z equals 0, and we have the two media with permeability and permittivity mu1 epsilon 1, mu2 epsilon 2, as we expect. So now let's talk about the two types of polarization. The two types of polarization that we're going to refer to are TE, or transverse electric, and TM, transverse magnetic. And the natural coordinate system for us to use is the coordinate system that has one vector pointed out of the plane of incidence and the second vector that makes up the right-hand triplet. Because remember, we have our direction propagation specified. If I define one polarization as being out of the plane of incidence, then the other polarization is then specified. Right? So the two states are either parallel or perpendicular to the plane of incidence. We're going to define the transverse electric polarization state, or the TE state, as the one that has its electric field orthogonal or perpendicular to the plane of incidence, and that's what's drawn over here on the right. We've got the wave polarized out of the screen. The plane of incidence is in the screen, so the wave is coming out of the page. Right? And the electric field is completely perpendicular. The magnetic field, of course, is defined. We know that once I've defined the electric field and the direction of propagation, that then the magnetic field direction is specified, and it's shown here in red. So here I have the electric field out of the board, and I've got the magnetic field vector pointing down and to the right in order to form the right-handed triplet. Now, Because I've got the electric field pointing out of the plane, the reflected electric field and the transmitted electric field must also be pointed out of the plane. There's no way to introduce the other polarization states. It's orthogonal. There's no mechanism to mix these together when I have an interface between two simple materials, right? Linear, isotropic, and homogeneous materials. So what I've done here is I've specified that all three waves, the incident wave, the reflected wave, and the transmitted wave, have their electric fields pointed out of the plane of incidence. The magnetic fields are pointed in different directions, as you can see, and that's determined by the direction of propagation. The electric fields, in this particular case, when we go to the interface, the electric fields are all in the y direction, which means that all of the electric fields are tangential to the interface between the two materials. On the other hand, the magnetic field has a tangential component and a normal component, and that difference is going to affect how boundary conditions come into play. On the other hand, we can define a transverse magnetic wave. A transverse magnetic wave is defined so that the magnetic field is orthogonal to the plane of incidence. If the magnetic field is orthogonal to the plane of incidence, then the electric field is parallel to the plane of incidence. So we're referring to these as TE and TM, but you will also hear people say parallel and perpendicular. The state we're looking at now is parallel polarized. And some of you may study optics. In optics, we refer to them as S and P. Those are shorthand for the German words for perpendicular and parallel. But the S state is the perpendicular polarization to the TE polarization, and the P state is the state that's parallel to the plane of polarization as the plane of incidence as we're looking at now. Notice something here. The way that we've chosen our electric field is such that when these angles go to 0, so if I bring theta incident down to 0, the incident electric field and the reflected electric field are the same, and we're going to capitalize that on normal incidence in the next lecture. Of course, since we specified that the magnetic field, and once we specify the electric and the magnetic field, we know the other field, and in this case, the fields are transverse magnetic, and that's why we call it TM. Likewise, since our H field is only in the y direction, the reflected and transmitted H fields can also only be in the y direction. And I do want you to take special note. The incident wave, the magnetic field is assumed to be out of the page, right? But because of our choice of direction for the electric field, the reflected magnetic field is defined to be into the page, so that we get E cross H gives us the direction of propagation. Whereas the transmitted field is out of the page, in the same sense as the incident polarization. Okay? Unlike the previous example, we have the opposite here. At the interface, at z equals 0, the magnetic field is completely tangential. So we're going to apply the tangential H field boundary condition. The electric field, on the other hand, has both a tangential and a normal component. It's got a component parallel to the interface. I'll draw that. It's got a component parallel to the interface, and it has a component perpendicular to the interface. And we're going to need to take that into account when we're applying the boundary conditions. Let's consider now the case of reflection and refraction for the transverse electric polarization. We've got three waves, an incident, reflected, and transmitted wave, and we can specify the fields in this way. We're stating that the incident fields are polarized in the y direction. We see that here. Propagating with wave number beta 1, and the direction is given by, has a component related to sine theta in the x direction and cosine theta in the z direction, and we can check that. If theta goes to 0, right, then this vector is propagating in just the z direction. The sine theta would go away, cosine theta would be 1. Right? If theta were 90 degrees, cosine theta would go away, and sine theta would be 1. And so that's our check. The reflected field is propagating with angle theta r. The direction has reversed for z. We've gone from a plus sign here to a minus sign here, but it's stayed the same for x. Same wave number because it's the same material. And the transmitted fields has a different wave number because we're now in medium 2. So here's medium 2, whereas these guys are both medium 1. And the direction of propagation is both plus x and plus z, traveling with the angle theta t. So the first step we're going to do is we're going to define the reflection and transmission coefficients. And we're going to say that the reflected field is written as the reflection coefficient times the incident field, and the transmitted field is the transmission coefficient times the incident field. So now we're going to be solving for gamma and tau. We've written everything in terms of E incident. The whole problem will scale as the amplitude of the field changes. The next thing we're going to do, since we know the electric field and we know the direction of propagation, we can write the magnetic fields, and we have the expressions here. Here's my magnetic field incident. It's got a negative x component and a positive z component related to the angle of incidence. Right? If the angle of incidence were 0, then the magnetic field would be purely in the x direction, minus x direction. The amplitude is given as E incident over eta, right? Because that's our definition of the wave impedance for a plane wave, and it has exactly the same propagator. So you'll notice that these propagators below are exactly the same as the propagators above. Likewise, the reflected magnetic field has a positive x component and a positive z component, and the transmitted magnetic field looks like this. Note, of course, that the transmitted magnetic field is using wave impedance eta 2 because it's a different material, and it's also using wave number beta 2. So the next thing we're gonna do to help us is we're gonna evaluate this at z equals 0. So when we evaluate it at z equals 0, all of that z cosine theta term goes away, right? And we're reduced down to just the x term. That's all that's important to us. And then the next step is we're gonna apply Snell's law. Remember, Snell's law tells us that beta 1 sine theta incident equals beta 2 sine theta transmitted. And it also tells us that theta incident equals theta reflected. Right? So I've replaced all of these propagators by e to the minus j beta 1x sine theta incident because they're all equal to each other. If you actually want to do a mathematically rigorous definition of Snell's law, we define Snell's law from a conservation of momentum argument. But if you want to do a mathematically rigorous definition of Snell's law, this is the step you would do it. The only way to satisfy the boundary condition is if all of these terms are equal. And so that's a mathematical statement of Snell's law. Now we're going to enforce the boundary conditions because we know that's how we deal with this sort of a problem. And so at the dielectric interface, we need to have both the electric and the magnetic field's tangential components be continuous across the boundary. Right? On the left-hand side, I've got the incident and the reflected component. And on the right-hand side, I have the transmitted component. If we recall, our incident electric field was completely tangential to the interface because it was in the y direction. For the magnetic field, though, it's only the x component that matters. The z component is normal to the interface, and that's got a different boundary condition that we're not exploiting. We're just exploiting the tangential boundary condition at this point. We could use the normal boundary condition if we wanted, but it will be a normal boundary condition on B, not on H. Right? So on the left, I have the sum of the incident and reflected. On the right, I have the transmitted for both the electric and the magnetic fields. I'm now going to substitute in my reflection and transmission coefficients, so I just get rid of ER and ET by putting in these values that we've already assumed. So now we can solve for the reflection and transmission coefficients. Get rid of the amplitude. We don't care about that amplitude anymore. And so now we reduce ourselves down to the following two equations that we need to solve. We've got 1 plus gamma equals tau. And down below for the magnetic field, we have a slightly more complicated expression. Because we're only dealing with the x component of the field, we've got the cosine theta that comes into play. And so the amount of the magnetic field, which is polarized in the x direction, is going to depend upon the incident angle. As the incident angle changes, that direction of that vector changes, and more or less of it is normal or tangential to the interface. You'll also notice that we have the sign difference because of our definitions. Whereas the electric field was always in the plus y direction, the magnetic field actually changes its sign here. And so we have a positive sign here, I'm sorry, a negative sign there and a positive sign here. We can eliminate the transmission coefficient in this bottom equation, right? So in the previous step, I had tau here, but I can say tau equals 1 plus gamma. And that's what I had there. I also, looks like I got through a minus sign. I also multiplied by -1, and I'm down to this equation here. And then I can solve for gamma. Once I've solved for gamma, I can solve for tau. And these are the two expressions that I end up with, gamma TE and tau TE. And I'm plotting these. For this particular case, the index of refraction, and the medium 1 is free space, and medium 2 has an index of refraction of 1.5, or equivalently a dielectric constant of 2.25. So we can see here that the reflection coefficient starts at 0.2 and goes to some larger value. The transmission coefficient starts at 0.8 and goes to 0 as I go to grazing incidence. As I go to grazing incidence, right, so here's my interface, my incident wave goes like this. The wave just skips off the interface and nothing gets in. So the reflection coefficient goes to 1, the transmission coefficient goes to 0. I'm actually going to walk you through the steps. Sorry, my chair squeaks. I know it squeaks. I'm actually going to walk you through the steps for the TM polarization case. It's very much the same, but there are some key differences, and the reflection and transmission coefficients are different. So I am going to go through each step. If you feel overwhelmed by the derivation, just relax. You don't need to memorize both. Important thing is you remember what comes out at the end, but I am going to go through the steps. But I'm going to go through more quickly because it's pretty much the same process. So we have TM polarized fields. Now the magnetic field is in the y direction. The electric field is in the plane of incidence. The magnetic fields for the three waves are given as such. So the incident field is polarized. Incident field is in the y direction, has amplitude E incident over eta, propagating with the same propagation constant we saw before. The reflected field now has to be pointed in the minus y direction because of our conventions that we chose, because of the directions we chose the electric field to be in. And we have E cross H gives us propagation up and to the left. And the transmitted field is over here. Notice, of course, that we're using eta 2 and beta 2 in medium 2, whereas we're using eta 1 and beta 1 for the incident and the reflected fields. Again, we're going to define the reflection and the transmission coefficients. Right? But now we have gamma TM and tau TM. And since we know H and beta, since we know the magnetic field and the direction of propagation, we can write down the electric fields. And the electric field expressions are given here. Right? You see the electric fields have positive X components, and they could have positive or negative Z components, depending upon which wave we're considering. Again, we'll evaluate at Z equals 0. So the Z cosine theta terms goes away, and we apply Snell's law. Right, so we end up with all these exponentials having the same value, and we're going to be able to divide them out when we get to that step in the satisfying for the boundary conditions. Once again, we're going to use tangential E and tangential H boundary conditions, but this time it's a little bit different. The H field is in the y direction. So the entire incident, entire reflected, and entire transmitted magnetic fields are all tangential to the interface, whereas it's only the X component of the electric fields that are tangential to the interface. We'll write down what we know. We substitute in gamma and tau. So we have this expression here. We divide out the E incident field intensity, and we're left with these two equations. 1, 2, that we can solve for gamma and tau. Right? We'll be able to solve for tau and substitute it in down below as we did before. And we have now got an expression for gamma that we can solve. Once we solve for that expression for gamma, we plug it into this equation, and we get an expression for tau. And these are the results. And you see something very interesting here. Okay. So we've got the reflection coefficient, eta 2 minus eta 1, eta 2 plus eta 1. You see the reflection coefficient starts at 1.2 and then goes up to 0.8. Actually, this will continue going all the way up to 1. Looks like I've accidentally clipped the plot. This will continue going up and intersect here at 1, where the transmission coefficient will go to 0. Notice something very interesting. For this range of angles, the reflection coefficient is negative. Then at this special angle, the reflection coefficient goes to 0. We'll talk about that in just a second. And then for this range of angles, the electric field is positive. And so that actually is an indicator of a flipping of the electric field. It has to do with the effective impedance of the interface when I take into account the direction of propagation, which is an advanced topic that you don't need to worry about. The thing you have to remember is that for this TM polarization, we have this transition through 0. So that means that there's going to be a change in polarization state upon reflection or transmission from an interface. We're going to assume that the two materials are both dielectrics for this simple conversation. mu1 and mu2 are equal to mu0. And that we have index of refraction 1 and index of refraction 1.5. And I'm plotting here the TE and TM reflection coefficients. And I should note this is actually the magnitude of the TE and TM reflection coefficients, because we saw that the TM reflection coefficient actually goes like this, starts negative and comes up and has a 0 crossing. But when I plot its absolute value, it comes down and goes up. Notice these two are the same at an angle of incidence of 0. And we're going to see in the next lecture at an angle of incidence of 0 or normal incidence, I can't differentiate the two polarization states. There's also a difference in the transmission coefficient, but it's not as pronounced. But what this tells us is if the incident field is purely TE or purely TM, then the reflected and transmitted fields are purely TE and purely TM. But if the incident field is a mixture of TE and TM, as I've shown down here. So here I've got the incident field that's in part TE, part TM, with the unit vectors that define those two directions. Then the reflected fields have changed. So whatever the relative value of ETE and ETM were, they've now been changed by the reflection coefficient. So that means the polarization state has changed, as we saw in the previous lecture. Likewise, the polarization state of the transmitted wave can change. And there's one very special case. The very special case is the Brewster angle. The Brewster angle is this angle here, where the reflection coefficient for the TM case is going through 0. So if the reflection coefficient is 0, that means for TEM, and the reflection coefficient is non-zero for TE, that means that the reflected wave is purely TE polarized. And we can actually use this to make a polarizer. It's used in optics regularly to make a very high quality polarizer. Right? Talk a little bit about what's going on here. By the way, this is satisfied. We can go back to the previous slide. We can go back to the Fresnel coefficient. It's satisfied when this numerator goes to 0. Right? So when A to 2 cosine theta transmitted equals A to 1 cosine theta incident, that's when I have the Brewster angle. Okay. And we can solve for this by doing some trigonometric substitutions, and this is the value that we get for the Brewster angle. And the physical explanation as to what's going on is very interesting. What happens here is the incident wave comes in and the reflected wave comes off theta r equals theta incident. Okay? And here's my transmitted wave. And when I look at this transmitted wave, that transmitted wave is polarized in this direction. Right? So that's my direction of polarization of my transmitted wave, which means that at the surface, the bound charges are going to be oscillating back and forth in the direction shown here by these arrows. Right? Intuitively, if I have an electric charge oscillating in this direction, that's going to radiate sideways, but it's not going to radiate in this direction. That may actually not be intuitive to you. You're going to see that in the last section of the course when Greg talks about antennas. Right? But it's a fundamental property that when I have an oscillating dipole, it radiates sideways and not out the end. And so what that means is, from a physics standpoint, is that the oscillating charge at this surface cannot produce any electric field for the reflected wave. And that's sort of an intuitive explanation as to why at the Brewster angle for this polarization state you have no reflected wave.
The last special case that we're going to examine is going to be the case of total internal reflection. We talked about total internal reflection last set of lectures in lecture 6, and we know that when the index of refraction in the second medium is lower than the index of refraction in the first medium. So for example, when I'm going from glass to air or from water to air, that I can have an instance when the sine of the transmitted angle, which is given by n1 over n2, and n1 is greater than n2, so this number here is greater than 1. And so once the incident angle gets to the critical angle, then the sine of the transmitted angle is greater than 1. And when that happens, the cosine of the transmitted angle is purely imaginary. Let's see what this means in the context of the Fresnel reflection coefficients. What we have is a situation where cosine of theta incident is purely real, right? So we'll call this A. And cosine of theta transmitted is purely imaginary. So we'll call this I times B. It doesn't matter what A and B are for what we're going to say. So I have a purely real number, in this case minus I times a purely imaginary number. And in the denominator, I've got that same purely real number plus I times that same purely imaginary number. So if I look at the magnitude of the numerator divided by the magnitude of the denominator, I have A squared plus B squared square root. That's the magnitude of the numerator divided by the square root of A squared plus B squared. Okay. So the magnitude of gamma TE and the magnitude of gamma TM are both going to be equal to 1. And we see that play out here. And so what I'm showing you here is an example of where I've computed the reflection coefficients for TE and TM polarization for the opposite of the case that we just saw. So this is going from glass into air instead of from air into glass. And we see that, again, at normal incidence, the two reflection coefficients are exactly the same. Right? Remember, of course, that this TM reflection coefficient actually started negative and crosses 0 here at the Brewster angle, right? But their amplitudes come down, they go to a null here for the TE polarization case, and then comes back up. But then at the critical angle, here at this critical angle, we see that the magnitude of the reflection coefficients are both equal to 1. But let's take a look at the phase. Remember, we said over here that I had A minus IB, or JB, over A plus JB. Okay, so this is going to have a phase angle. Right? These are actually complex conjugates of each other when I plot them in the z-plane. Right? So there's going to be a phase angle associated with this ratio. And what I'm plotting here in the bottom graph is the phase angle associated with the reflection coefficients. Now, a couple things. For values of theta less than the critical angle, we see that the phase angle of the TE reflection coefficient is 0. Right? So that means in this particular case that it's positive. The phase angle of the TM reflection coefficient starts off as being 0, but then switches to being 180 degrees. So that means that it went from being positive to being negative. And in this particular case, because we're going from a high index material to a low index material, the TM reflection coefficient actually starts positive and then becomes negative and goes to -1 in this particular instance. Okay. But then we see for these two reflection coefficients that once I exceed the critical angle, so here's my critical angle for this particular geometry, there's my critical angle, I can see that there is a phase shift that's introduced between the two polarization states. So here I have equal amplitude. So they both have amplitude of the reflection coefficient of 1. All of the power is reflected. But there's a phase shift introduced between the two polarization states. And when there's a phase shift introduced between the polarization states, that means that if I have linearly polarized light that's incident on this interface with both TE and TM polarizations, I'm going to introduce a phase shift between them. And it turns out that total internal reflection is a mechanism that is used in a particular type of geometry to convert linearly polarized light into circularly polarized light by capitalizing on this phase shift so that you get an exactly 90-degree phase difference between horizontal and vertical polarization. When you get that 90-degree phase shift, you end up with circular polarization, as you saw in the previous lecture. So this is a long lecture, but it covers some important tough stuff. Remember what I said. It's not important that you be able to reproduce those derivations. What's important is that you be able to use those Fresnel reflection and transmission coefficients. On any sort of an examination, you will be provided them. You will not be expected to memorize them. You do need to know what all the parts are. You need to know theta incident, theta transmitted, theta reflected. You need to know Snell's law, but then you need to understand how to use those to calculate changes in polarization state, the amount of power that's reflected and transmitted. So in the tutorial, we're going to look at computation of the critical angle, computation of the Brewster angle. We're going to look at what happens for reflection and refraction. You're going to look at evaluation of the Fresnel reflection coefficients, and for the tutorial problem that you have, I might suggest that you try to do that evaluation numerically. You can write out the formulas, but you can only take that so far. You can just plug it into MATLAB and get the plots. And then we're going to do something looking at power flow when we're at the critical angle.